The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball, as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy, it's moving outward, but eventually there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now what I did the focus on was a V equals 12.
There it is, yeah. Okay, that's the right star. We have
Get a better focus now, that was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine. We're looking back in time to study distant galaxies, seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat. But when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of the lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, he's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift is the cornerstone of the quest to pin down the fate of the universe. Clearer pictures of the universe that have only been possible in recent years have led cosmologists to conclude that the redshift of distant galaxies is greater than predicted. This is startling. Not only is the universe expanding, it's speeding up. Nothing in the observable cosmos could account for an accelerating universe, and yet the data seem irrefutable. This has to mean that an invisible force is working against gravity. Cosmologists have come up with a name: dark energy.
So when the universe was young, gravity was the most dominant force. And so what we see here is galaxies as particles on the surface of the water are bound together by gravity. And at a point about 7 billion years ago, dark energy and gravity are pretty well in balance. But the universe continues to expand, the density goes down, and so dark energy starts to take over. And lo and behold, the universe starts to accelerate. So dark energy is now the dominant property of space.
So the universe started out with a certain amount of energy, and we know we're trying to understand how much energy there is, and we know the universe is expanding as it moves outward with time. We also know now that the universe's expansion is accelerating, and we don't know, is that acceleration going to slow down or not? We're still trying to understand that. So in understanding what's going to happen to the fate of the universe, we have to know how much energy is there, how much matter is there.
The history of the universe is really a battle between dark matter and dark energy. These two forces are in opposition, and so both the history of the universe and its ultimate fate is really the competition between these two forces.
The Big Crunch theory was a result of scientists interpreting that dark matter is the dominant force. But astronomers now suspect that dark energy might be much stronger. If so, the end could be dramatic and violent.
It pulls apart solar systems, it pulls apart stars, and eventually it grows so strong that it pulls apart matter itself, breaks bonds, pulls apart atoms, and reduces everything to fundamental particles, and that's the end of the universe.
The battle between dark matter, the force that holds the universe together, and dark energy, the force seeking to tear it apart, has set the universe on a path of destruction. If dark matter is the victor, the universe might collapse, If dark energy rules the cosmos, it could rip to shreds.
The expansion grows so strong that it tears up the entire universe.
It'll be a strange twist of fate. Dark energy, the force that propelled matter to form a magnificent universe, continues to push it outward and drives it to its demise. To find out if dark energy is in fact winning the battle, scientists will first need to know how fast the universe is actually expanding.
The most remarkable feature of the universe is that it's expanding. Every galaxy is moving away from every other galaxy. When you look out into the night sky, you see distant stars, galaxies, clusters of galaxies they observe with telescopes, and they're all moving away from us. We can illustrate that with this balloon. As we expand it, we see that every dot drawn on this black balloon, like the night sky, is moving away from every other dot. But there's something else that we know about the universe, something else that we know about the expansion. That is that the expansion is getting faster. The universe is accelerating. The size of the universe is getting bigger at a faster and faster rate. And we don't know exactly how fast it's accelerating, but if it's accelerating fast enough, then something really dramatic could happen. The universe could end up tearing itself apart in a big rip.
This is perfect. This is great that you rigged this up. So this is a giant version of the demo that I do in class.
Dr. Robert Caldwell attempts an earthbound experiment to show how dark energy affects the acceleration of the universe. He uses a paintball gun mounted on a truck.
Yeah, and basically, I mean, we could adjust the angle in any way that you want it. What do you think about this?
I think down at the
down
ground,
a little bit more
is the best, so we can mark each
How's
time
that?
the gun fires. That'll be good.
Let's try that.
He sends the truck coasting down an incline. Earth's gravity pulls the vehicle downhill, which is similar to how dark energy propels the universe outward, causing it to expand. Gravity pulls the truck forward at an increasing speed. The gun fires paint at the ground at regular 1-second intervals. Caldwell measures the distance between the paint dots to calculate just how fast the truck was accelerating. He'll use the data from this experiment to see how gravity's force compares to dark energy's force in the cosmos.
We started thinking about the Big Rip when it was discovered that the expansion of the universe was accelerating. The degree of acceleration is not known, and it's the subject of a lot of effort by astronomers today to try and figure out exactly how fast the expansion is growing. What is the past evolution of the universe in detail, and if we can glean from that, what is the future evolution of the universe? It's not known exactly how fast it's accelerating. There's some evidence that the acceleration is beyond a certain threshold, and beyond that threshold, there's a runaway effect that could take place, and it would rip apart the universe.
Good luck.
Fantastic. I think we've got some good data.
Excellent. How do we measure this?
Great. Give you that end.
All right.
I'll take this.
5 feet 8.5 inches.
The point of the paintball experiment is to find parallels between the truck propelled by the invisible force of gravity and the accelerating universe.
I'm glad we got the long tape measure because it's really growing pretty fast, the interval.
Within a few measurements, the distance between the paint spots increases by nearly 7 times. If the truck were in space, at this rate, it would travel faster than 100 miles per hour within a minute, and over 1,000 miles per hour within 10 minutes.
They're getting big now.
Here we got 42.5 feet.
42, all right, 0.5.
The question for Robert Caldwell is whether the same kind of expansion and acceleration are happening on a cosmic scale.
What's the capsule made of? Is it plastic or something?
Gelatin.
Uh-huh,
It's
okay.
all biodegradable.
Uh-huh.
So you could actually eat them if you wanted to.
This right here is the data that I took with Eric, the cumulative distance traveled by the car as a function of time, and that's beautiful. It's this nice parabolic shape. That's exactly what you expect for an accelerating body. Now over here I've got another calculation going on where I'm working out the acceleration of the universe.
Robert Caldwell's calculation shows that forces on Earth are similar to forces in space. This demonstration, then, gives a sense of the dramatic rate of expansion that appears to be happening in the cosmos.
By eye, it might be difficult to appreciate how good a fit it is, but I can tell you that the weight of the statistics indicates that an accelerating universe is a very good fit to this data.
If, like the truck, the universe is continually accelerating, then billions of years from now, the universe might tear itself apart.
All the distant stars and galaxies will be pulled away from each other. They'll be pulled away from us. But moreover, we won't have time to grow cold and lonely. It'll actually be pretty exciting and dramatic and violent. Stars are ripped apart, planets are ripped apart, and even atoms are torn apart before the universe ends. It wouldn't happen for at least 50 billion years, but still it's an interesting fate for the universe.
What would atoms ripping apart look like? Things like coffee cups are solid. Atoms join together to create something that will hold a cappuccino without leaking a single drop. Zoom in through the cup, like sailing through the cosmos, past the molecules and into the atoms. The solid cup is nothing more than a fabric of atomic particles that formed a bond to become matter. If these particles were to move apart, the bonds that hold this cup together stop working. The atoms no longer support molecules. The connections between the minuscule particles dissolve. Matter in the form of this cup ceases to exist. It disintegrates, gone from existence. This is the dramatic end that Robert Caldwell foresees for the universe.
What you would see if you were standing on Earth or standing on some other planet that happened to still be around at that time, you would see something that looks like a wall of darkness approaching you. And as the wall of darkness approaches, stars would go out, galaxies would go out, and then eventually that wall of darkness would surround a planet. And then pretty soon, atoms themselves are torn apart, and that's it. Just the wall of darkness shrinks down to a point, and that's the end of the universe.
According to Robert Caldwell, that moment is still billions of years off, leaving plenty of time to refine the research.
In a way, this is like a detective story. We're trying to figure out what is the culprit, or who is the culprit responsible for the cosmic acceleration. We think we know its name. We call it dark energy, but we don't know the modus operandi. We don't know exactly how it works. And what's needed is more information about the physics behind the dark energy. We want to know exactly what it does and exactly what it's made out of. And in answering those questions, we'll be able to figure out exactly what is the fate of the universe.
The Big Rip is one theory. Cruising just above Earth's atmosphere and peering deep into space, the Hubble telescope provides scientists with clues to a less violent, but equally unavoidable, end of the universe. Scientists now say the universe is expanding, and that depending on how fast it is accelerating, it might end in a big rip where everything tears apart. It's also possible that it will continue to expand, but at a slower rate. The universe wouldn't rip apart, but would become dark, cold, and lifeless.
If dark energy turns out to be constant, a constant property of space, and continues at the same rate that it is now, the universe will keep expanding forever, and it will be a very sad state. I think in the end, it just chills out. Everything cools down.
Evidence for the Big Chill and all of the theories for the end of the universe, in part, come from the Hubble Space Telescope. It has been orbiting Earth since 1990 and has an unobstructed view of the cosmos. The extraordinary images it beams back to Earth are amazing in their clarity and detail. And because of Hubble, scientists can make better predictions about how the universe will end.
So here is an example of a very deep field that was taken by the Hubble Space Telescope. Literally, you point the space telescope at a single region in space. And if you looked at this from a typical ground-based image before Hubble was launched, first of all, it's literally almost size of a postage stamp. And so suddenly, the first Hubble Deep Field that was ever taken had 4,000 galaxies that looked just like the galaxies here, that were never visible before from the ground. A tremendous power. Each of these smudges in their own right is another galaxy. Each one of these galaxies contains about 100 billion stars.
Hubble sees more than just stars and galaxies. It just might be on to one of the key ingredients of space, an invisible ingredient that could put the brakes on dark energy's effect and cause a big chill. That's dark matter. Scientists talk about dark matter as the substance that holds the universe together and could prevent a big rip. Evidence that dark matter exists is seen in some of Hubble's images of nearby galaxies. It sometimes appears as though other galaxies surround them. The other galaxies are not really there at all. Rather, they are reflections of more distant galaxies coming from behind. Astronomers suspect this optical illusion is dark matter causing a weird distortion of light called gravitational lensing. The light from the more distant galaxies is literally bent by the curvature of space caused by stars and dark matter in its path. The more dark matter there is between Earth and the distant galaxy, the more the light will be bent and the greater the force to cause a big chill.
The gravitational lensing is a tremendous tool for the astronomer because we can measure the distortion in background galaxies and use it to trace the distribution of dark matter on various scales. We're looking at a distribution of idealized galaxies here on the sky, and the light from these distant galaxies is passing through clumps of dark matter. What you look at is not really what's happening. It's a bit like wearing spectacles and not knowing that you're wearing them.
And if you can tell how much that bending is occurring, you can map the dark matter, and you can also see, well, if there's dark matter there, is the universe around that dark matter behaving the way it should given the gravity or not? If it's slightly gravitating less, then dark energy might be changing in those places.
Identifying which energy force dominates, dark matter or dark energy, will give scientists more confidence about whether a big chill or a big rip will be our fate. The best evidence shows dark energy as the driving force, but by how much? Solving this mystery depends on astronomers finding ways to measure how fast the universe is moving. On Earth, it's simple to determine how fast something moves. An airplane, for example, is relatively close. We can look at it and calculate its speed by estimating the distance it travels and timing how long it takes to get from one point to another. But a star's light can travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces in stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the Big Chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a Big Chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward. Dark matter slows them down. In a Big Chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter, and much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place. But in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
We assembled all those difference measurements and make a map of what the variations look like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?
4.6 billion years ago, our sun started to form about 2/3 of the way out on one of the spiral arms of the Milky Way. Our sun is a third-generation star, starting from gaseous clouds and dense nebulae containing many heavy elements. It condensed under the inexorable pressure of gravity until it was hot and dense enough to experience nuclear fusion at its core. As stars go, our sun is an average yellow star. But it is so massive that it contains 99.8% of all the mass in the solar system. Its radiant energy supports almost all life on Earth, and it drives Earth's climate and weather. It is almost 900,000 miles in diameter. It has a core temperature of about 15 million degrees, and its surface temperature of about 6,000 degrees. The sun will be fairly stable over the next 5 billion years, at which time it will enter its red giant phase. It will expand enormously so that its outer layers will reach the current orbit of Earth, giving it a diameter of almost 200 million miles. After that, it will live a few billion more years as a white dwarf. Mercury is the smallest planet in our solar system. It is only about 3,000 miles in diameter and has a surface that is pockmarked with craters like our own moon. It is the innermost planet and has an elliptical orbit that takes it within 28 million miles of the Sun at its closest approach, and out to 43 million miles at its most distant. It takes Mercury 88 days to orbit the Sun. And figure this out, sports fans. Although it rotates once every 59 days, the day on Mercury is 176 Earth days long. Oh, it doesn't really have a tail. We added the one in the video to make it easier to see and to show its orbit. And although the scale is correct for the size of the Sun relative to Mercury's orbit, we are showing the planet 100 times larger than it would be if it were to scale as well. Except for the Sun and the Moon, Venus is the brightest object in the sky. And since it is closer to the Sun than we are, it shows phases like the Moon. Shrouded in permanent clouds, Venus rotates on its axis every 243 days, and it rotates backwards from the other planets. It is only slightly smaller than the Earth, and it orbits the Sun every 225 days, at a mean distance of 67 million miles. But its surface is terribly inhospitable. The atmospheric pressure at the surface is 92 times that of the Earth, similar to the pressure a half a mile down underwater. Its temperature is a balmy 900 degrees Fahrenheit. All in all, not a good vacation spot. Our Earth is 8,000 miles in diameter and rotates on its axis, causing sunrise every day. It is the largest of all the planets that have a solid surface, and it possesses an unusually large moon for a planet of its size. Since the moon circles the Earth, we think of the moon's motion as circular. But since the Earth-Moon system revolves around the Sun at about 65,000 miles per hour, the moon's motion in the solar system isn't much different from our own. At 93 million miles from the Sun, the Earth is the third innermost planet, and is the only place in the solar system that we know of that has liquid water. Mars is the planet most similar to Earth in terms of habitat. Although smaller than Earth and Venus, it has a thin atmosphere and probably had liquid water on its surface in the past. This attracts our interest and has prompted us to send a plethora of probes. It has 2 orbiting irregular-shaped rocks graciously called moons, which are probably captured asteroids. A day on Mars lasts about 24 hours, very comparable to our own. The volcano called Olympus Mons, or Mount Olympus, is the highest known mountain in the solar system. It is an extinct volcano and is over 3 times the height of Mount Everest. Mars is the 4th planet from the Sun and completes its orbit every 2 Earth years. Jupiter is huge. If it had only been a little larger, it could have become a brown dwarf star circling our Sun. It is a gas giant and has no solid surface. Its atmosphere forms bands of poisonous clouds that circle the planet in opposite direction. The giant red spot is a huge storm that has been raging for hundreds of years. 4 of its many moons are so large that Galileo spotted them with his primitive telescope in 1610. In addition to moons, all of the gas giants have rings, but Jupiter's rings are so faint they are not visible. The 5th planet out, Jupiter orbits the Sun at a distance of 480 million miles and takes almost 12 years for one complete circuit. Notice the large separation between the orbits of Jupiter and Mars. This is the realm of the asteroid belt. It is the debris of a planet that failed to form because of Jupiter's gravitational influence. Saturn is the 2nd largest of the planets. Only Jupiter is larger. Like all the gas giants, it has a system of rings. And the rings of Saturn are glorious. Like Jupiter, Saturn also has dozens of moons, and one of them is particularly notable. Titan is the 2nd largest moon in the solar system, and it possesses an atmosphere remarkably like Earth's. It is primarily composed of water ice and rocky material. It is even possible that under the clouds and surface ice, Titan has liquid water and maybe even microbial life. It is 50% larger in diameter than our own moon and 80% more massive. Saturn takes 29 years to orbit the Sun, and does so at a distance of 890 million miles. Uranus rolls on its side. It is an icy giant of a planet, the 3rd largest in the system. Like the other giants, Uranus has a ring system and numerous moons. It is the 7th planet out, and it orbits the Sun at a distance of 1.9 billion miles. A year on Uranus lasts 84 Earth years. Because of its extreme axial tilt, seasons on Uranus are worth a look. At the time near the solstice, one pole continually faces the Sun, while the other faces away. Only a narrow strip near the equator experiences Uranus' 17-hour day. At the other side of Uranus's orbit, the orientation of the poles is reversed, so each pole gets 42 years of continuous day, followed by a 42-year night. Okay, let's head to a point high over the ecliptic, so we can see the relative sizes of the orbits of the sunward planets. Neptune is a blue world. It is the smallest of the giant planets in our system, but still 30,000 miles in diameter. Since the demotion of Pluto, it is the furthest planet from the Sun. Neptune's rings are very faint, and of its 13 moons, only Triton is massive enough to be round. It rotates every 16 hours and orbits the Sun every 165 years at a distance of 2.8 billion miles. Pluto is now deemed a dwarf planet and a member of the Kuiper Belt. The Kuiper Belt is a region of the solar system that extends just beyond the orbit of Neptune, at about 2.8 billion miles out to about 5 billion miles. Like the asteroid belt, it is crammed with many small bodies orbiting the Sun, most of which are frozen methane, ammonia, and water. Here's a size comparison. Earth, Ganymede, Titan, our Moon, and several bodies from the Kuiper Belt. Currently, the largest known Kuiper Belt bodies are Eris, Pluto, Sedna, and many more without formal names like FY9 and EL61. A day on Earth is a deceivingly simple concept. Today we'll examine that day on Earth in detail, perhaps uncovering a few surprises. A day is the length of time it takes the Earth to spin 360 degrees on its axis. Or is it 361? Here is a simple model showing the Earth, the Sun, and some background stars. The Earth travels around the Sun in an ellipse, with the Sun at one focus. The model, of course, is not to scale. Let's begin our examination at noon one day. The Sun is directly above the red line. That will be our reference point. Watching from a high vantage point, we see the Earth complete 360 degrees of rotation. But during that time, the Earth has also moved a bit in its orbit. So even after a 360-degree turn, the Sun is not directly above the same point on Earth that it was at the beginning of the spin. It is not noon of the next day. The red reference line needs to spin a little more than 360 degrees to get us to noon. The 360-degree rotation is called a sidereal day, while the noon to noon rotation is called a solar day. Earth orbits the Sun once for about every 366.26 sidereal days, and once for every 365.26 solar days. Not only that, the length of the solar day varies throughout the year, and for two different reasons. First, because of its orbit is an ellipse and not a circle, the Earth moves faster when it is near the Sun and slower when it is further from the Sun. So the little extra amount of rotation that the Earth needs to do to get from noon to noon changes throughout the year. Second, because the Earth is tilted on its axis, the little extra rotation to get from noon to noon is largest at the solstices and smallest at the equinoxes. So solar days grow progressively longer as we move from the equinox, March and September, to solstice, June and December. And did we mention the Earth's spin is slowing down? And the length of the solar day is increasing due to gravitational tides between the Earth and the Moon? The length of the mean solar day is increasing at a rate of approximately 1.4 milliseconds every century. 2 billion years ago, there were about 750 days in a year. Now let's talk about daytime. That period out of 24 hours when it is light outside. Day versus night. Due to refraction and scattering of light by the atmosphere, there can be daylight even when the sun is slightly below the horizon. But day length is usually about the sun's disk being on or above the horizon. So the day begins the moment the sun's disk appears during sunrise, and ends the moment the sun's disk disappears during sunset. At the equator, daytime and nighttime are equal to within a few minutes. But at distances north and south of the equator, the length of the day varies with the season, with the longest and shortest days being on the solstices. At the poles, once the sun has risen, it stays up for 6 months before it sets again. And during the course of each day, it travels in a complete circle around the edge of the sky. Because the Earth travels at different speeds in its orbit, the sun is north of the equator for almost 4 days more than half the year, and the length of the average day in the northern hemisphere exceeds the length of the average day in the southern hemisphere by a few minutes. In the northern hemisphere, the Arctic Circle is the southernmost latitude where 24-hour daylight can occur at least 1 day in a year. In the southern hemisphere, the Antarctic Circle is the northernmost latitude where 24-hour daylight can occur at least 1 day in a year. And daylight savings time is like the old man who cut off one end of the blanket and sewed it on the other end to make it longer. A year on Earth is measured by one complete trip around the sun. Seems simple enough, but there is a problem. The Earth doesn't travel in a path around the sun that returns to its starting point. So how do we know when a year starts or ends? Well, one way, called a sidereal year, measures our orbit against the distant stars. As viewed from the Earth, our orbit causes the sun to appear to move through the constellations of the zodiac on a path called the ecliptic. And when the sun returns to its starting point, a sidereal year has passed. This motion is difficult to observe directly because the stars cannot be seen when the sun is in the sky. However, if you look at the sky before each dawn, the annual motion is very noticeable. The last stars seen to rise are not always the same, and within a week or two, an upward shift can be noted. As an example, in July in the northern hemisphere, Orion cannot be seen in the dawn sky, but in August, it becomes easily visible. Measuring a year this way gives a period that is 365 days, 6 hours, 9 minutes, and 10 seconds long. Another possibility is to measure the year against the passing of the seasons. Because of the tilt of the Earth on its axis, the position of the sun in the sky changes from day to day throughout the year. If we were to take a picture of the sun at noon regularly throughout the year, we would see the sun moving on this path called an analemma. On the days in its orbit when the Earth is at a maximum tilt towards or away from the sun, the length of the daylight is at a maximum or a minimum. These days are called solstices, and the sun will be at the top left or bottom right of the analemma. On the days when the Earth's tilt is perfectly sideways to the sun, the day and night are equal in length. These are the equinoxes, and the sun will be at a latitude-dependent position in the analemma. When the sun goes from one vernal equinox to the next, a tropical year has passed. Measuring this way gives a year that is 365 days, 5 hours, 48 minutes, and 46 seconds long. The length of a year on Earth is affected by several gradual and cyclical changes in its orbit and its tilt. First, there is the precession of the Earth's axis. Over a period of about 26,000 years, the Earth's axis traces out a circle in the sky. One result of this is that the North Star changes over time. Right now, the Earth's axis points towards Polaris. 5,000 years ago, the axis pointed to a star in the constellation Draco. And 12,000 years ago, the brilliant star Vega was the pole star. And because of the 26,000-year cycle, Vega will be the pole star again in 14,000 years. The precession of the equinoxes is caused primarily by gravitational forces of the sun and the moon acting on the Earth. While the axial tilt is the primary cause of seasons on the Earth, the distance from the sun, which changes throughout the year because of the elliptical shape of the Earth's orbit, contributes a small bit of temperature variations throughout the year as well. When the axis is aligned so it points towards the sun during perihelion, one hemisphere will have a greater difference between the seasons, while the other hemisphere will have milder seasons. The hemisphere, which is in summer at perihelion, will receive much of the corresponding increase in solar radiation. But that same hemisphere will be in winter at aphelion and have a colder winter. The other hemisphere will have a relatively warmer winter and cooler summer. When the Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, the northern and southern hemisphere will have similar contrast in the seasons. At present, perihelion occurs during the southern hemisphere's summer, and aphelion is reached during the southern winter. So the southern hemisphere seasons are somewhat more extreme than the northern hemisphere seasons when other factors are equal. In addition, the gravitational effects of other planets cause the ellipse of our orbit to slowly spin around the sun. It takes about 112,000 years for the ellipse to revolve once, relative to fixed stars. When considered together, the two forms of precession add, and it takes about 21,000 years for the solstice to go from aphelion to aphelion. The dates of the perihelion and the aphelion advance each year on this cycle, an average of 1 day per 58 years. The eccentricity of the Earth's orbit is a measure of how round or how oval the orbit shape is. Over thousands of years, the eccentricity of the Earth's orbit varies as a result of gravitational attractions among the planets, primarily Jupiter and Saturn. The orbital eccentricity cycles with a period of roughly 100,000 years. As the eccentricity of the orbit evolves, the semi-major axis of the orbital ellipse remains unchanged, so the length of the sidereal year remains unchanged. As the Earth travels in its orbit, the duration of seasons depends on the eccentricity of the orbit. When the orbital eccentricity is extreme, the seasons that occur on the far side of the orbit are substantially longer in duration. In addition to axial precession, there's the axial tilt, the angle the Earth's rotational axis makes with its orbital plane. It is currently about 23.4 degrees and is declining. This tilt varies from 22.1 degrees to 24.5 degrees. It makes one complete tilt and back every 41,000 years. This change in tilt is directly related to ice ages on Earth. The last maximum tilt occurred in 8700 BC, and the next minimum tilt will happen in 11,800 AD. The inclination of Earth's orbit drifts up and down relative to the present orbit, with the cycle having a period of about 70,000 years. And the orbit also moves relative to the orbits of other planets as well. By calculating the plane of unchanged total angular momentum of the solar system, we can define the orbital plane called the invariable plane. It is approximately the orbital plane of Jupiter. The inclination of the Earth's orbit has a 100,000-year cycle relative to the invariable plane. This 100,000-year cycle closely matches the 100,000-year pattern of ice ages. A year on Earth is directly determined by all the various orbital motions of the Earth. So, if someone tells you how many years old they are, you might ask them, is that sidereal, tropical, or anomalous years? Want to see something really big? Well, watch this. Our starting point is our own moon. We've seen men walk on the moon, and it's pretty big. But even the smallest planets are bigger. Here are Mercury, Mars, Venus, and Earth. And the gas giants in our solar system are huge in comparison. Here are Neptune, Uranus, Saturn, and Jupiter. And of course, our sun makes even Jupiter seem small. But let's look at some really big stars. Here's Sirius, and Pollux, and Arcturus, and Aldebaran, and Rigel, and Deneb, and Antares, and Betelgeuse. And the largest star we currently know about is VY Canis Majoris. On this scale, our sun would be 1/10 the size of the tiny little dot you see to the left. We know mass distorts space. We know light is affected by gravity. And we know Einstein's theory of general relativity makes possible one of the strangest objects ever imagined by physicists. If you could create a large enough distortion in space-time, by placing enough mass in a small enough space, you could create a region of space-time so strongly curved that nothing not even light, could escape it. And since nothing can travel faster than the speed of light, anything that entered this region of space-time would be trapped there until quantum mechanical effects allowed it to escape. Black holes can come in any size and have any mass. All that is required is that enough mass can be concentrated to the point where it collapses under its own gravity. Stellar mass black holes are formed when stars 20 or more times the size of our own sun finally run out of fuel in their cores. They rapidly cool and collapse, and the shockwave from the collapse blows the outer layers of the stars to bits in a colossal explosion called a supernova. But the small, dense core of the star can remain bound together by the force of gravity. As it continues to collapse inward under its own weight, the atomic particles of the core are smashed together until all that is left is a black hole. In its center lies the singularity, the mass of an entire star crushed into a single point in space. Surrounding that is an invisible shell called the event horizon. This is the cosmic point of no return. Once inside the event horizon, nothing, not even light, can escape except through quantum mechanical processes. Supermassive black holes may contain billions of times the mass of our sun. These monsters lie at the center of every large galaxy. Micro black holes have tiny masses at which the effects of quantum mechanics are very important. Black holes of this type have been proposed to have formed during the Big Bang and would quickly evaporate due to said quantum mechanical effects. At the end of their life, it is believed that they would emit a sudden burst of energetic particles, but no such bursts have been detected as of 2008. We can never see into or directly know about what happens inside the event horizon of a black hole. In effect, any object that crosses this imaginary line has left our universe for good. But if nothing, not even light, can escape a black hole, then how do astronomers manage to detect them? It is possible to imagine spotting a solitary black hole by observing the bent starlight from behind it. But a better chance of detecting one would arise if they were not alone in space, but accompanied by another star. This black hole is drawing matter from a companion star, which orbits it at a distance safely outside the event horizon. As the gas spirals into the black hole, it heats up and emits huge quantities of high-energy radiation. Intense radiation emerging from a small area, or stars orbiting small invisible companions, these are telltale calling cards of a black hole. $12.5 billion years ago, the universe was littered with the remains of first-generation stars, and billions of second-generation stars were born from these clouds. Small groups of these new stars were drawn to each other gravitationally and merged to form ever larger and larger groups. Our own galaxy, the Milky Way, is an example of a spiral galaxy born in this early era. Today, it contains about 200 billion stars and is still growing as it absorbs small neighboring clusters of stars. The center of our galaxy is in the direction of the constellation Sagittarius. And like most large galaxies, there is a monstrous black hole at the center. The disk of our galaxy is about 100,000 light years across, and on average is only about 12,000 light years thick. Our own sun is a third-generation star and is located about 2/3 of the way out on the spiral arm named Orion. We are about 26,000 light years from the center. The Milky Way is a member of a group of 20 or 30 galaxies and star clusters called our local group. The largest galaxy in this group is our sister spiral galaxy, Andromeda. Is it possible for distant galaxies to be moving away from us faster than the speed of light? And if it is, would it be possible for us to see them? Surprisingly, the answer to both questions is a resounding yes. How is that possible? How can something travel faster than the speed of light? Today we will try and paint an accurate picture of the universe based on the lambda cold dark matter model, which is the best cosmological model today. Once we have painted that picture, the answers to our questions will be straightforward. Let's assert that some kind of space-time quantum foam sort of something existed before our own universe began, before our Big Bang. Then we simply let Heisenberg's uncertainty principle go to work for us. If we look at the tiniest speck allowed by quantum mechanics, a small volume with a Planck length as its linear scale, the speck would have a volume of 10 to the minus 99 cubic centimeters. And the largest amount of mass or energy that we could put in this volume without it becoming its own black hole is about 1/100,000th of a gram. Interestingly, the uncertainty principle allows this much stuff to be created out of nothing for as long as 10 to the minus 43 seconds. Not a very long time, but it will prove to be enough. Because if that much energy is created in the form of a certain type of scalar field, then we have just successfully created a universe. The best model of how our early universe grew after that initial quantum fluctuation created it includes inflation, a period when the scalar field divides space into a brief period of extreme exponential expansion. During inflation, space erupted from its tiny beginnings into an unknowably huge volume. This enormous expansion generated an enormous amount of gravitational binding energy, at least 10 to the 85th grams. And this was counterbalanced by a corresponding group of positive energy in the scalar field. What began as a mere fraction of a gram of energy has now become 10 to the 85th grams. This is a huge number, large enough to account for all the matter and energy that exists today. But notice that the total energy in the universe is within a quantum fluctuation of equaling 0. As a byproduct of the enormous growth of space during the inflationary period, tiny quantum fluctuations grew into macroscopic fluctuations in the density of the scalar field, making it ever so slightly lumpy. This lumpiness provided the seeds for the formation of stars and galaxies and all the structure we see in the universe. At the end of inflation, the temperature throughout all of space was still enormously hot. But as space continued to expand, it cooled, and the energy of the scalar field, which now filled all the new and enormously huge volume of space, decayed into dark matter and dark energy and normal matter. The photons and quarks and electrons, which in turn settle down into the protons, neutrons, and atoms that populate the universe today. After about 380,000 years of expansion and cooling, charged particles got together to form neutral atoms. And suddenly the photons that were bumping into charged particles every second or two were free to zip unhindered across space. This is the origin of the cosmic microwave background that we see today. Let's let this volume of blue dots represent all of space at that era. Then let's focus our attention on this tiny portion that has a radius of about 42 million light years. This is the region that will be all of our observable universe in 13.7 billion years. Our Earth will form somewhere in the center of this region in about 9 billion years. But we have a lot of expansion to experience first. Imagine that you are standing on a 100-meter track and someone 99 meters away is going to walk toward you. There's the starter's pistol, and the walk begins. But there's a problem. The track is stretching, growing longer as he walks. He takes a 1-meter step every second, but the track grows 1 meter for every 100 meters every second. After 10 seconds, the walker has taken 10 steps, but the remaining 89 meters has grown so that he still has 98 meters from you. Another 10 seconds, and he's still almost 97 meters away. It will take him 460 seconds, but he will eventually reach you. And during that time, the track is stretched so that it is now 10,000 meters long. The other end of the track is now moving away from you much faster than the walker can walk. If he had to start there now, he would never get here. And the question of how far he walked is ambiguous. We could say he walked 99 meters because that was the distance at the beginning, or we could say that he walked 9,900 meters because that was the distance at the end, or we could say 460 meters because that is his normal speed times the time it took. The expanding universe exhibits the same characteristics. Light from the edges of the 42 million light-year sphere began their journey to the spot where the Earth will develop about 13.7 billion years ago. But during the trip, the intervening space multiplied itself 1,090 times. And now the spherical shell from which the light began is about 46 billion light years away. This is the farthest into space we can see right now, and it is called our particle horizon. 100 million years after inflation, the first stars formed. They were massive giants that formed in every region of space, including our little sphere of observable universe. Those that formed on a shell a little inside our expanding particle horizon are just visible today. The light from these primitive giants has been traveling over 13 billion years. And the shell of space where they formed is now over 36 billion light years away. So light from the microwave background was emitted from a distance of just 41 million light years away. And that distance is now 46 billion light years. And light from the earliest stars was emitted from a distance of 1.5 billion light years. And that has grown to 36 billion light years. Due to the faster-than-light expansion of space in those early years, the light was actually moving away from us for billions of years before the slowing expansion allowed it to start moving towards us. Light we see today from some distant galaxies that was emitted from 5 to 6 billion light years away comes from objects that were the most distant at the time the light was emitted. Massive objects like the Earth and the Sun, that are gravitationally bound to one another, can overcome the expansion of space between them. Space is expanding in our system, but the distance from the Earth to the Sun does not change because of this expansion. Why? Because as space expands, the Earth's orbit continually adjusts to keep the Earth at the correct distance that is demanded by the law of gravity. This is also true for stars inside a galaxy that are gravitationally bound, and is true even for local clusters of galaxies. As space expands, the distance between the bodies constantly adjusts to comply with the laws of gravity. The wavelength of light from distant objects is shifted toward the red end of the spectrum if they were moving away from us. And the expansion of space is measurable by measuring the redshift. And unlike the Doppler redshift, the cosmological redshift says nothing about the recessional velocity of the emitting object either at the time the light was emitted or at the time the light was received. Hubble's law says the further away an object is, the faster it is receding without limit. So, there are always objects far enough away to be receding faster than the speed of light. Objects we see with a redshift of about 1.46 are moving away from us at the speed of light, and all objects with larger redshifts are receding faster than the speed of light. Most objects in the extended universe are traveling away from us with velocities fast enough that we will never see them. In effect, we have an event horizon, and events beyond our event horizon are effectively unknowable to us. Objects that have a current redshift of about 1.8 are currently about 18 billion light years away, and are now crossing our event horizon, never to be heard from again. Finally, this is a time sequence of the evolution of our universe. Big Bang, followed by inflation, reheating or the birth of matter, birth and death of the first stars, and the ongoing formation and growth of galaxies. When we look out into the universe, we're looking backwards in time, looking at the universe as it was when it was a lot smaller and a lot younger.